It is our great pleasure to have a seminar by Professor Euihun Joung from Joung University. I think that everyone knows him. He's an expert on higher spin and gravity. And today he will talk about colorful gravity in lower dimensions. Yeah, please.
Thank you very much. May I take off now? Thank you. Thank you very much first for the invitations. So I will talk about colorful gravities in lower dimensions. So before start, let me begin with some of the motivation. So people thought about the various extensions of gravity. So here, usually I would put the subura first, but here maybe I can put first. The right place for that. And then supergravity, subura, and higher spin. So this can be viewed as some extensions of gravity, in the sense that we have here we have G mu and B mu, and then the here G mu, and then that is a shear field. In the case of higher spin, we have G mu and then some higher spin fields. More fields. So those these extensions of gravity share some features in the sense that we have some symmetry which is relating to these fields. In case of supergravity, we have supersymmetry. This is relating those fields. And in case of DFT, we have ODB symmetry. In case of higher spin fields, we have a higher spin symmetry. So let me resume. So in case of higher spin gravity, we have a higher spin symmetry, which mixes the various fields. So colorful gravity can be also viewed in the same way. So we can think this of a multiple graviton, multi-gravity. In this case, we can consider maybe some spin-to field H mu, but many spin-to field. And those things can be also related by some global symmetry. So this, the colorful gravity that I will introduce is a kind of multi-gravity which shares the same features with other type of extensions. Yes. So for me, this was a sort of a good toy model to study some problems of higher spin gravity as well as other models. So, and then so there was, so usually when I talk about this colorful gravity or multi-gravity, people just comment about talk about novel that they heard about. So maybe I can mention something about this novel. Yeah. Actually, what happens is that so people try to construct multiple gravity using this starting from H mu, which is free method system. So you put many different copies, and then you put reactions with some other terms, and then try to add interaction terms. So this way, people try to construct multi-gravity theory in the past, and then some vertex. And then they found that if we introduce such interactions, the case invariance of the model, because original method spin two fields has a certain gauge symmetry. Otherwise, we will have, if this gauge symmetry is broken at the interaction level, we will have some problems with diffusion freedom. That's why when we add interactions, the gauge symmetry that this original free fields head should be deformed in certain way so that we still have the same symmetry, same gauge invariance. So that's the prediction is that the V is essentially this cubic interaction, essentially same as that of your Einstein group. But with this vector, some symmetric vector. So this result, if I remember correctly, there was originally Ward and company, and then Macano and Nicolas Boulanger who worked about this no-go theorem. And then, so this implies what? This implies actually what we see is that whenever we have some construct certain good cubic interaction, from that we can extract global symmetry because free theory has originally H mu has this free gauge symmetry from which we can already extract the Killing tensors and the that Killing tensors. And then if we have information of cubic interactions, this cubic interaction defines a Lie bracket for these Killing tensors, and then we can already obtain some good structures, Lie algebra structure for this global symmetry. And then the condition is that this global symmetry should be really closed. But then what people found is that okay, this global the global symmetry given by multiple gravity is generated by same kind of generator as the gravity case, for instance, translations and then Lorentz, but this time with the multiple generators. And then commutation relations, Lie brackets are already determined, but that's the same as the Einstein gravity. So for instance, if I write down same kind, this Lorentz thing, you should have the same Lorentz structure. It means an M eta axis, rho, mu, sigma. But I have K and then with the T, I, J, K. So this was people found that okay, whenever you consider more than one copies of free methods in two, and then when we add any interactions, this interaction should be something similar to the Einstein gravity, and then this theory should have global symmetry, but this global symmetry is already is subjected to this form. But then, because of these particular structures, we found that if you so that is this no-go. This no-go is that if you don't add any other generator, if you just work with this generator, that means that if you consider only free massless spin 2, that pi mu m mu I alone no non-trivial. This was the logo that you may have heard about. So essentially, here trivial means that you can have a global symmetry, which is just different copies of this isometry, which commit to each other. And essentially, the theory is just multiple copies of Einstein gravity, which do not talk to each other. That's trivial situation. Apart from that situation, there's no other solutions. So that's the no-go that was known. But there is also yes-no. So we can actually, you can have a non-trivial symmetry if we add more, and then plus more generator means more fields, more gauge fields here, and then which may help to close this algebra. So typically this more can be infinitely many. So one simple example is high spin gravity. High spin gravity can be extended in a way, simply in a way that it contains more than one copies of gravitons. So typically we need to add infinitely many more generators, but lower dimensions, it is possible to add minimize this. So this is what I will talk about. So in higher dimensions, maybe not all the cases infinitely many more, but anyway, it should contain much more rich structure here. But in case of lower dimension, actually what we need is just to that I will explain. Any questions?
Do you have any motivation to study this?
Yeah, I think that this it can be considered as a good toy example of higher spin gravity or any kind of multiplications of gravity. Non-trivial number. So that was also one motivation. Yeah. And one also interesting scenario is that maybe so we can have many massive spin too, but there is some symmetry breaking pattern which actually can be obtained in ADS3 model. And in some cases we have only one massive spin 2, and then all the other get masses because of symmetry breaking. So that kind of scenario can be also.
So graviton can have mass.
It can acquire MS. Yeah, through this spontaneous symmetry breaking. Not all the model, but in the model of ADS3 that we have considered some time ago, that have such mechanism, but sort of slightly limited, but yeah, it has such.
It's interesting because I heard to have consistency from island conjecture, some people like Aju require we need to require some massive gravity.
Yeah. So anyway, in string theory, we have many massive spin 2 states. So maybe it's another way to see how those states emerge. Because if we take tensionless limit, all those things should become massless. So then now let me begin with the constructions of such global symmetry. So essentially what we can do is that we can think about the generator M a mu, which is a symmetry generator. I want to make this way with I. Then actually I can think that in this way. It can be viewed as TensorFlow of the original symmetry, some Lorentz or translations, and then some other global symmetry. So then you can think whether this is this makes sense. But then actually, when you have this kind of structures, we have all the time this anti-commutator. So from this, we can see that in general, this does not make sense. So if we cannot define these things, then we cannot define this commutator or this kind of simulators. But some cases it's possible to define this object if it's okay. If mu is associative. That means that if I can embed our original isometry algebra into an associative algebra, then the construction works. So this can be done in a minimal way. ADS2 and ADS3. In ADS2, we have isometry SO1, 2, and ADS3, the isometry group SO2, 2, which is SL to R, and then this is again SL to R cross SL to R. The algebra. So here it's easy to extend these guys to GR to R, which is asymptotic matrix, combined matrix, and then we can define this just single associative product. And again, these guys into just a GR to R, GR to R. So because when we add this, we need to add one additional generator, which is identity. That's actually called for, that's explains this additional guys. So and then so for TI we can use just UN. So in this way, you see that what we can do is essentially GL 2R times UN. This is as colored asymmetry. Here maybe and then it turned out actually this is nothing but UN combined. UN combined. And then we can also truncate these guys. After doing all these constructions, we can also truncate this to ON. Then this will become ON combined, maybe.
GL is non-compact,
GL is non-compact.
but the U is a compact group.
Right.
Yeah, so is there any difference, difficulty in defining colorful isometry geometry? So either way, U or so you can choose either group.
You mean whether I can replace this UN to the other guys?
I mean, so GL times U is a non-compact group.
Yes, it's a
But
non-compact.
the UN is a compact group.
Yes.
So the common wisdom is that actually gravity,
Yes.
actually relevant group is a non-compact.
Right.
But the UN,
Here, this is non-compact.
U is non-compact.
UN comma N is non-compact.
UN, non-compact.
This is like a Lorentzian versions of this equilibrium group. So yeah, so this is like that, and then eventually this guy becomes UN comma N, or in this case, this guy becomes UN comma N, then plus UN. Yeah. So this will be the setup. So let's take UN comma N. So inside there, how many different generators? So first the GL has identity, and then the other generator, let me call it MU. Just here, maybe I should do it this way. to see what kind of generator that we have here. From U side, we have again identity. Another generators of SUN generator. So then we see that I times I some diagonal U1. And then the other thing is that mu I plus mu ti and then plus identity ti. So this is the structure. So what we can see is that this is something dummy which commit to anybody. So if you see that this, if you make some gauge theory out of it, you will have some gauge field which do not interact with the other thing. So we can just drop it. So then this becomes a SUN. And then this is usual isometry. Original isometry. So it's like it gives gravity. Usual gravity. There's no code. And this SUN gauge. And this is very peculiar U of Z, which is colored. Because we have gauge field, and then this is a joint in this gauge group. Colored into passes into. So what we see is that already from this algebra level, we can predict it pretty much. We see that there is some group given by this much, and this much, which is precisely SL2R, and then SUN is some group subalgebra of UN. And then we see that this is just gravity, and this is just usual SUN gauge fields. So they are just sitting there. And then there are other kind of gauge field, which is some strange guys, which is behaving like metal spin 2, but they are somehow charged with respect to gauge fields, SUN gauge fields. So and then we are curious what we can have, what kind of relativity theory that we can obtain. So we can just look either one option is consignments. And then just take A bar. Now, so this takes value in SU and comma A. So then you can do the usual trick, like so you rewrite down some Simon theory in this way, and then so according to this kind of decomposition of generator, if we expand that or rewrite the theory and then just remove spin connections, etc., then we really see that the 3D gravity and then SUN Simons, and then coupled to some strange guys. Nicely spin 2, which has some potential, by the way, and then this potential has some strange minimum, and then it can have some symmetry breaking patterns, etc. So this guys, Simons A and A. You can just solve spin connection, etc. We can obtain just the usual Einstein gravity. UN Simons. So they don't talk to each other because this is gravity. They are not, they commute. So this fact is reflected here. But now we have some strange metal sector that are called chi. This guy has some kinetic term which has d I mu, which has usual nabla, but and also with the A. So it is gauged with respect to gravity as well as to other SUN gases. And then it has also potentials. It has this guy has contains potential, which is a type to force potential. And then you can see there is some many strange, many saddle points, and then depending on the choice of saddle point, we can have symmetry. So this was something that I did some time ago already. So I will be quick at this point, and then I will move to the other things that I did more.
So Chon Simon has only one derivative. And
Right.
how can you have two derivatives?
So again, here so I need to solve some spin connections.
So
Spin connection.
some auxiliary,
Yeah, auxiliary field.
like Palatani.
Yeah. So certain component of A, I just remove. I just solve. Treat as auxiliary field.
And this meta Lagrangian has there should be some metric to contract indices, and
Yes.
that metric is nothing but
Yeah, this one. Yeah. So actually, when we do this work, at first we did a really brute force, like term by term, and it was quite difficult to analyze. But at some point, we understood actually it's pretty much everything is dictated by these structures. This is just commutator between this is just this way. So this is some subalgebra B. This is another C. Essentially, this is UN, and there's a B part and C part. And then D is subalgebra. And then D, C is just C. So with this property, we can pretty much easily massage these expressions, and then we can just derive more or less easily this covariant derivatives from this case structure.
But on the resulting action,
Yes.
so how does FL2R appear? Is it a local Lorentz symmetry rather than diffusion?
Right, it's local Lorentz.
But you don't have here pure by, you have metric.
So no, so this we have two copies of SL2R. So the usual P plus J and then P minus J. So and then J is local Lorentz.
But is you have only metric, no pure by or dry by?
So originally we have, because this is
But on the
A is like typical.
but on the resulting action.
Yeah, resulting action we can remove omega, so then we can end up with G.
Then I cannot see GL FL2R local Lorentz symmetry.
It's sort of
All they are all
yeah.
singly. All
Well, like gravity, we know that Poincare plays certain role here.
yeah, but if you have only bosonic metric theory, metric is singly on the local Lorentz symmetry.
Metric is right.
Yeah, so it's
Local Lorentz is not.
so is it same here?
Yes, same.
I cannot see FL2R unless I decompose metric into pure by.
Right. So SL2R, this kind of thing is hidden in this two derivative theory as global symmetry that we can see, but as a sort of gauge symmetry of gauge fields, that kind of interpretation I think we cannot need to do more gauge field formulations to see the role of such this kind of global symmetry as well. So this was something that I did a long time ago with the Joung Wei and And then Christian. And then we did also the computations of asymptotic symmetry. And then this time, so there are two more things that I want to talk. Recently, I did also this particle, or if you like, colorful particle. So in a sense, it's particle counterpart of this gravity theory, or some sort of the matter which may couple to this theory, but the particle was not really. So this I did with again Karapet, Christian, and then other homies. And then more recently we did this BF formulation, BF gravity, or if you like, stative gravity.
So the particle has a FUN index.
Particle has right SUN index. Stative gravity and let me make. This is with Euihun, and then Schwarzian-like. This color particle actually, this the other people were interested in making use of this Maxwell algebra. They were making some infinite extensions of Poincare algebra, but which can explain somehow the charged particle. It's called Maxwell algebra, and they were curious about sort of Yang-Mills extensions of such things. And then somehow, so they are interested in this kind of constructions. It turned out that it's slightly different from this Maxwell algebra, but nevertheless we proceeded. And then for me it was fun because I learned many things, many elementary, but I see useful things from project. So that I can sketch. So here what we did is flat space versions. Flat space versions of this SUN, SUN. So it's SUN comma N. It's contraction, so it's like adjoint representations and just taking contractions. So in this way, we have a certain set of a generator like this, the two copies, because we have in 3 dimensions. But the computation legend is slightly different. But what we did is that actually Joaquin Gomez is expert in this non-linear realizations. So that is making particle actions out of some isometry, some symmetry. So let me sketch very briefly how it works for usual Poincare, and then we also sketch for this color case. So actually, yeah.
A Schwarzian action,
Yes.
number 1.
Yes.
The left-hand side, actually, as you know, Schwarzian theory is there's no local dynamic degrees of freedom.
Right.
But the right-hand side, you generate the real degrees of freedom. So
No, actually, this is also so that's why it's an interesting model, but still it's something like toy model. This is SUN Chern-Simons, no degrees of freedom, and this is no degrees of freedom. And this is also massless spin 2, so it does not have any freedom.
really?
Yeah, but just its charge.
어.
And then what happens is, interesting point is that is actually because of the potential, we can have some kind of Higgs mechanism. Then actually this guy is part of this spin 1. But those are both do not have any bulk division freedom. But then nevertheless they combine, and then they become the new field that's called psi mu. Some other type of non-propagating field, but we can see that it is a 3D analog of what is called the partially massless field. Partially massless. Yeah. In digital space-time, we have this mass spectrum. So spin 2 field, if you have a massive like spectrum, M square, digital space. So then, if you from the massive spin 2, if you reduce the mass, then there is some gap. This is a huge bound. So this is massless. And then if you reduce, then you cannot smoothly reach to the massless field from the massive spin 2. And there is this bound. And on this bound, this is PM, you still have some sort of, your field acquire certain gauge symmetry. And then what is decoupled is only the scalar mode of massive spin 2. So essential degrees of freedom is that of massive spin 2 plus massive spin 1. So that is what's happening here in general. In the ADS, we can also have the same thing, but it's not. But interestingly, that kind of pattern we can observe. But the 3D analog, so it's not proper. This nonlinear realizations. So this thing is for me. Eventually, I understand it as a quad-zone orbit. So actually, currently I'm working on this in more general ground, and then we managed to find the way to get any particle actions from any using this data. So if you have any symmetry, then or any, so that's just unpublished for all. I will not say too much about advertising words. So anyway, so this is quadrant orbit tricks. Essentially, what we do is like that. We have when you have a Poincare symmetry, which is P mu and then M mu. Then so this is you go to the quad-zone space, which is a dual. Like let me call it a dual space. Then this dual space, we can act the quad-zone action, then it forms an orbit. And if you select a certain orbit, then this orbit, from that orbit, we can make some particle action, whether automatically. So that's the thing. How we do? So we can directly write down the actions. The action looks like this. And the phi is just the element in the I as well. So Poincare this, and then G is Poincare. So then what we can do is that if I take phi as m times p 0, then this section will give directly after some computation we get actually t root p square plus m square dx 0 plus p this kind of expression. If we add the t,
But this is a flat background.
yeah, flat background. Yeah, so I did the first step. So then we can introduce some auxiliary field and to make it more We introduce E to make it more covalent form. But in this case, actually, we need to double the orbit. So plus minus here the definite sign. So we add the positive, both add the combine positive and negative. And we have this because if we solve these things, clearly we have plus minus solutions. Zero is plus minus. Here becomes 0. So this setup, maybe I will skip. Just we can do in a straightforward manner, and we immediately arrive at this, and then we can add sections. So here again, this section is in the. If I write only P plane, P surface, then clearly M, so it's just the usual momentum orbit. But to get these guys, we need to include the negative energy orbit. So now what I can do is that I can use color extend the 3D isometry. So what I do is now use SU n comma n SU n comma n as algebra, and then do the exactly the same thing. So here. So the generator is like P mu and mu. This is original three-dimensional algebra case, but we have in addition this color guy, and then some sort of UN. In this case, so we have this kind of algebra. And then phi we take again same thing, 0. And then we can compute. And then we can compute, and then we can obtain some expression which is quite ugly. But at some point we can realize that actually we can again use this trick of adding some auxiliary Lagrange multipliers to make it more symmetric. Then eventually what we get is deceptions. X and P is SU n elements, and then N is UN element. But in a sense, it's somehow color extension to this algebra, this Lagrangian. Although this is matrix form, it's not obvious. But if you take n equal 1 case, then you can easily see that you can just rewrite this in this form. P 2 by 2 matrix, typical P alpha, alpha dot, and that kind of notations, you can just rewrite this section to this one. But the more general case, we have more general. Yes.
Change your marker.
Your choice of phi
Yes.
seems break Lorentz symmetry, but action is not the resulting action is not dependent.
Right. It does not depend on the choice of phi, but choice of the orbit. If we, so here I took this vector, but if I take this vector again, the action is the same. It does not depend on that. So just it depends on the choice of you. So here again, n equal 1 case, reproduce uncolored case. N equal 2 is a simple example, and then n equal 2, and then if you do the space analysis, then what that happens is that, like in this n equal 1 case, which contains 2 orbits, in this case, it has 3 orbits. Like quote unquote, looks like one is like this and the other is like that. Although I cannot draw it this way, but like cartoon image, I have another orbit. Based on this kind. Three orbits. And then general case. So we have n plus 1 orbit. So this is also some interesting points. This is actually related to your work with Kevin. Mathematically.
But before, n equal 1 is still SU 1,1.
Right.
2 by 2 by 3.
Right.
So you are saying it's the same as 1,1.
Right. 2 by 2 matrix, but there is no. So 2 by 2 matrix, we can use again this index alpha dot. Yeah, 2, and then it becomes the usual.
That
Usual
P and
treatment.
F does not have any.
Yeah, there is no index.
No,
No
no
index.
explain.
All those indexes in actually somehow encoded this matrix nature of that symmetry. So n equal 1 case typical trick of this component, and then you can rewrite it in the component form. So starting from n equal 2 and higher, it's more tricky to interpret in that way. Although in principle it's possible using this case. So actually what happens is that we can see that the 2 orbit, n equal 1 case, 2 orbit was originally we added only this guy. But the other orbit which is included by extending by modifying it Lagrangian into the form with the Lagrangian multiplier, we include plus and minus. So just we combine these two to have covariant matches. So for general cases, what happens is that we can write in a matrix form. There is a 2n by 2n matrix, and then there are number of 1 is here L, number of minus 1 is S. And then again here again 1. So anyway, so we can relatively easily identify what are the other orbits which are included in these sections, which is actually just a choice of sign, because actually we can just change the positions, just the number of negative signs. So this way we can easily count, and then it turned out that we can relatively easily identify what is this orbit. So usually this quadrant orbit is like that. When you have this quadrant space, and then when you have this vector, you add group element and then move. But some group element will leave this vector invariant. That will be stabilizer group, which is phi. Then typically the orbit given by this vector phi is just this quotient space. And in this case, the orbit, which is parameterized by this number L, which is running 0 to n, which is like L orbit is given by U n comma n, and then U n minus L L U n minus L. I guess this is familiar since to you. I think mathematically it's pretty much related to your classifications of this method of getting. So I don't have more time. 10 minutes. Yes. So let me move to the third part. Yes. Then Schwarzian. Again, we can begin with like Chern-Simons. We use a typical BF action, scalar field, and then field strength of a certain gauge field, and then we add some boundary term. That's constructions, and then F is just here. And then now we can use A text value in SU. That's it. And then now if you just we can mimic the usual thing that we do in the treatment of this JT gravity. The BF formulations of JT gravity. So that we add some other boundary conditions. Additional boundary condition. So U is the temporal coordinate. And this is typical thing that on the boundary we relate the scalar field and then the temporal component of the gauge field with some constant.
Adding boundary term is crucial.
Yeah, this yeah, it's a variation of principles.
Why don't you add in class 1 with Chern-Simons boundary?
Yeah, Chern-Simons theory there also it's important because there typically we impose some boundary conditions. I don't remember exactly, but specific boundary condition which so there are few more than one choice. One choice is that we add proper boundary terms and then we don't impose strong gauge. The second choice is we impose a relatively strong gauge and then that with that boundary condition we don't need to.
The result is here depends on the boundary.
So apparently this is not completely clear in the literature. Yeah. So again, here it's the choice of boundary term and boundary conditions. Although there are like 100,000 and 10,000 papers on this subject, it looks like it's not completely clear. That's my opinion. Okay, so if we do proceed, then what we get is this S is the boundary reduction. If we do the boundary reduction, that means that we solve verification of motions and then plug the solution into this. Then we get that and then twist AU square distance. And then so we need to evaluate this guy by solving F equals 0. And then boundary condition this and together with the asymptotic ADS boundary condition. This is typical things, and if we do, then we obtain the Schwarzian theory. That's what people have done recent times. Yeah, and many other people. So let me sketch very briefly the method, and then let me also sketch how we can do it in the cloud case. So typically we do this case. We solve this by pure gauge, choosing this pure gauge U, B, inverse to B, and then B is this point R as 0. 0 is our specific generators of SFR, and A is functions of U. B is this function of R. So this is solving all these conditions. Then now it's sufficient to determine A. And then so A itself is given by G like this, because it's pure gauge. Everything boils down to the choice of G, the functions of U. And then the asymptotic boundary condition, this is implying that A should have form L1 plus certain functions of U and then L minus 1. So this is a kind of ADS boundary data, and then this is subleading. Upon acting B, so in actions of B, this is subleading. So it's like that. Dominant in the boundary. So this is the kind of conditions. And then typically what we do is in the zero temperature case, maybe I cannot enter too much into detail. I can these Gauss decompositions. Then FDE is functions of U, and then I just solve these conditions. With the G, I compute A, and then I import this. Then just we get simple relations. And then the result I plug into S. Then what we obtain is just S is shorter. So Lagrangian here, L0. Yeah, here. Value becomes P inverse P minus square, and then P square is that. So this means just Schwarzian. This is something.
Oh, excuse me, what is temperature here?
Yeah, this is. So here the so we this is the local conditions, and on the boundary. So if we essentially this is the beta is the length of ADS boundary. So zero temperature means beta equal infinity. So it's the ADS boundary is infinity, then it's zero temperature. But if it's compact, then it's not. So yeah, so typical thing is we do this, and then in order to go to the finite temperature, there is some trick that people do. Just we put F equal tangent, sort of compactifying functions, if you like, and then we get the Schwarzian as functions of zeta, and then which is finite temperature Schwarzian. So that's something which is done in the usual gravity case. I cannot explain more. Yeah, so in the color case, color case. So what we can do is before what we understood is that actually this trick of just relating function f to zeta is equivalent to consider different decomposition instead of this Gauss decomposition. If I do like Iwasawa decompositions, then it works. So we had some relatively formal observation here, and with that observation, we could have a colorful Schwarzian both zero temperature and finite temperature. So that was also key observation, but probably I will skip that. But let me just sketch the usual basic things. So up to this point, it's the same. So what is different is just here. So we have the AU and L1 times I. which is just the L1 part, which is just the asymptotic boundary. We have only gravity. This is gravity which is defined the AD boundary. And then the rest we can put A. This is again gravity fluctuations. So dominant piece. And this is the spin 1 part which is orthogonal. And then N-1 TA. Okay. This is the color spin 2 contributions, which is orthogonal. So this is the minimum and all those are orthogonal. And those we can relabel as this much as J. And then this much you can call L. In this way, we can write a U as the identity and J, L, or IJ. So this is kind of matrix extension, or if you like color extensions of this set of A. And then if you do the usual computation, then actually you can obtain sort of matrix versions of the Schwarzian. Color the Schwarzian is maybe just let me give you just for an idea. Now it's all those guys becomes SUN matrix. Sometimes some of them is SUN Hermitians and some of them are just group value. But it's just sketch, so I will not explain the details. But there are some terms which is very similar. But this is sort of gravity piece, and there are spin 1 piece which is group value D. Here it's like spin S field on particle on SUN group manifold. And then there are coupling. Yeah, B contains actually both graviton and then this colored into, because the diagonal piece, singular piece is this into, and the other piece is so this has this color structures. And then we need to solve these conditions. Yes. In this case, it was easy because just I can put square root of that. But this is matrix conditions. Again, we have same kind of problems. Like when we analyze the orbit, we had many orbits, n+1 times the orbit, depending on the choice of signature, whatever. Again, because when we solve this theory contains a lot of different branches, which again has the same kind of mathematics as is the one that I showed in the particle. The probability of something related to this, and this mathematically. Okay, so this is the end.
Okay, let's get any questions or comments?
Can you imagine string the origin for this colorful gradient?
Again, that might be the only thing that I can think about is this tensionless limit.
Then you can have more than one spin 2.
Yeah, yes, but yes, massive spin 2, and then eventually, if you take a tensionless limit,
But is the original matrix spin 2 metric is still special? Here is it something like your particle action center of mass always coupled to that matrix spin 2?
Center of mass.
Yeah, center of mass, like the something.
So your X yeah.
Proportional identity.
In the particle model.
Yeah.
Particle. Yeah, that we didn't really consider yet. How those particles can couple to this model. So in principle, that can be studied.
Well, library looks like the equivalence principle is all broken, as you have many metric and many particles coupled.
Yeah,
to it,
yeah.
But maybe
this model. So there are several different some problematic issues. One actual issue that I didn't mention is some issues of non-unitarity. ADS models and also in the BF model case, it seems to have non-unitary natures hidden somewhere. But that's actually related to the spin-on part. So usually when we put the Chern-Simons, we never worry about the non-unitarity of Chern-Simons because the positivity of the norm is pure conventions. But when Chern-Simons somehow manage to couple with the other guys, but then we need to care. So apparently what happens is that this Chern-Simons or BF spin-on part that has it's a topological, but nevertheless it has some non-trivial norm, and it is split with respect to the gravity sector. So that was something that I didn't mention. So that's something that we cared about. Hewlett Presper, I didn't have it. So yeah. No.
In JT case,
Yes.
in the elementary JT case,
Yes.
the physical observer is usually told that it's a unit length.
Yes.
So how does it realize? Is it realizing this BF formalism?
Again, this should be something probably some sort of Wilson lines. Yes.
And so I'm always wondering how the gauge theory formulation realizes length in terms of Wilson line or something like that. Even in very major.
Yeah. I think I don't know well, but I know that the people use this Wilson line to compute various things, and even they claim that the Wilson line is the right way to do the same kind of analysis for higher spin case. So I think they do it that way.
Here, is there also some duality with the UN vector?
Yeah, this
Higher speed.
this multi gravity thing is relatively natural in this one case. So typical higher spin model is first it's due to the free ON, which is just preset, I think. But then what we see is that actually one easy way to understand these multiple copies of a spin, necessary spin 2 is just to decouple the sectors of CFT. Two CFT which do not talk to each other. And then they have a separate mu. So we can talk in this way. We can think in this way, but they start to couple slightly. Then actually certain combinations of T mu becomes genuine T mu, and the other becomes messy, or symmetry is broken. Bulk analog is the massive. It acquires mass. So actually, yeah. So this is somehow related in that business also. So whether we can understand this kind of mechanism in that way, but otherwise, people have considered some possible realization of this model. Also, they need a separate computation, offshore computations, and this CFT computations. and then they obtain the same asymptotic algebra that we obtain. That depends with but that's just some other cosine model.
Yeah, I have also an
Yeah.
elementary question.
Yes.
You told us that the algebra tells us the color of the metal is 2
Yes.
fields. But you mentioned that it gives us the Higgs-like mechanism. So I am wondering why
Algebra probably cannot tell that.
Yeah. So
Yes.
I am wondering why is it not a confinement but Higgs mechanism?
Confinement.
Yeah. Why not confinement? Usually non-apparent gas gives us the confinement.
Yes.
So I'm wondering why is it a Higgs mechanism, not a confinement?
But it's a Higgs mechanism in the sense that it's the combination of these zeros of freedoms. Just in that straightforward sense, it was like that. I thought about this confinement issue. Yeah, but I didn't proceed that much. So the idea was that actually, so what was that? So when in the ADS3 model, what is interesting is that the effective coupling constant depends on the vacuum state, the saddle points, and then when this Higgs mechanism or symmetry breaking takes place, I think all this color, only the singlet sector, the genuine gravity is weakly coupled, and the other things are strongly coupled. So indeed, in some sense, it can also might be related to this confinement. So I thought about that, but I didn't push that much. So the kind of although it's the toy model, but some scenarios like that. So it's some symmetric phase. We have all this method is spin 2, but when the symmetric breaking takes place, then we get only method spin 2. All the other is just confined and just.
Professor Moin has no question. You have invited Professor.
Me?
No. I mean the Moin Professor Moin has actually invited. So I'm wondering he's online, but he has no question. So if there is no more question, let's thank speaker again. 고맙습니다.